Cryptography. Cryptography is an interesting field of operation because in cryptography we have a whole lot of different functions that give us the ability to provide for confidentiality, integrity, availability, non-repudiation, and many, many other characteristics that are required to ensure that the data that's being sent is what is being received, and that the data being sent is hidden or confidential. All right? One of the first things that we talk about in cryptography is something called a cryptographic hash. A cryptographic hash. All right? It is a one-way function. And I saw this one time. This is a hash. This is my plaintext data. Tear it out. Right? Is it easier to tear that apart or put it back together again? Tear it apart. And that's basically what a hash is. Oh, wait, I needed that. No, kidding. All right. Hashing functions give us the ability, they're a one-way function, so they're a very simple mathematical operation that provides us the ability to do something. And it's a mathematical function, but it's very difficult to reverse. In fact, it's nearly impossible to reverse. You take an arbitrary amount of data, you run it through the hashing function. The arbitrary data that goes into the hashing function is called your plaintext, and the output is called your ciphertext. And this ciphertext output, it's also called a MAC, all right? Not media access control, but message authentication code. And that MAC is a fixed length. Okay, now there are two types of hashing algorithms that exist today. You guys know what they are? Two types. MD5, SHA. Okay? How does a hash work? Not mathematically, but what do we use a hash for? Message integrity. Okay, what does that mean? How can a hash be used to ensure message integrity? If I send you a letter and I want to ensure that that letter is not modified midstream, I put that letter through the hash. I come up with the MAC, message authentication code. I send that to the destination. I send the letter to the destination. You run the letter through the same hash, and if the hash matches, you've verified that the message has not been modified. A CRC, a cyclic redundancy check, is like a hash. So hashing does not provide encryption, at least not for the purpose of confidentiality. The sole purpose of hashing is to provide message integrity. All right? The other concept is this concept called the avalanche effect, where a small change in the arbitrary data in the beginning results in a massive change in the hash output on the end. That's one of the characteristics of a hash. A collision is described as the possibility that two different arbitrary lengths of data result in the same hash. And most hashing algorithms are relatively collision-free. In other words, any type of data that gets inputted is always going to result in a different kind of output hash. Now, I know this may not make complete sense right now, of course, we're going to go through this process and describe this in more detail, but this is only one function of cryptography, this hashing function. All right? Here's the problem, though. When you have a hash, what's to stop somebody from intercepting that data and modifying it and recalculating the hash? I mean, think about it. Here's your hashing function. All right? You got your data, which goes into the funnel. Out comes your MAC. Right? You send the data in plaintext along with the MAC. Now what's supposed to happen is the receiver at the other side is supposed to take that data, run it through the hashing algorithm. They're going to get a MAC, and they're going to compare this MAC to the MAC that was received. And that's what's going to be able to identify whether or not the data has been modified midstream. But wait a minute. These hashing functions are not hidden. They're not secret. These are open standard hashing functions. So if I'm sending the data along with the MAC, if somebody intercepts that data, if somebody intercepts that data and wants to modify it, can't they just simply modify the data, run it through the same hash, come up with a new MAC, and just simply throw away the old MAC and send that information over? There's nothing to stop that from happening. Follow what I'm saying? So, there's no authentication of the message. There's integrity of the message, but there's no authentication of the message. So the next thing that comes into play is something called a keyed hash. You'll often see this referred to as HMAC. HMAC. All right, so if you see MD5 HMAC, welcome back, Bernard. If you see MD5 HMAC or SHA HMAC, you know that this is a keyed hashing process as opposed to just a standard hashing process. How does this defeat the man-in-the-middle attack that we're talking about? You generate a hash, but when you throw the data into the hash, you throw the key in as well. That's your little secret sauce, right? You send that along the way. He's the attacker. He captures the data because the data is sent in plaintext. He modifies the data, throws it through the hash, generates a MAC. He's the receiver of the data. He's going to take the data, put it into the hashing function, but he knows your secret sauce, so he's going to throw in the secret sauce. The MAC is not going to match because him as an attacker didn't know the secret sauce. See what I'm saying? Bastard. I know. All right? So HMAC adds this concept of authentication along with message integrity. All right? Now, if you ever go into the CISSP later on, at least my CISSP class, not all of them do this, but we actually spend a lot of time on cryptography. We spend a lot of time on actually even doing the math behind cryptographic functions. Like AES, we break it down step by step. All of the functions of AES, how AES works and how it does its iterations and how it does its mathematical calculations, the mods. We even do some calculus in that class. All right? We don't do that in this class, though. All right? The secret key is only known to the sender and the receiver. It's not known to the man in the middle. So even though the man in the middle can intercept the data, there's no way that the man in the middle can regenerate a hash that's effectively verifiable because he doesn't know the secret sauce. Routing protocols use this method for authentication. EIGRP and OSPF use this type of method for authentication. You take the routing update, there's a shared secret key that you configure as an administrator that goes into the hashing function. We send the hash along with the routing update in plaintext. The router that receives the routing update sends that routing update through the hashing function with the key. All right, out pops the MAC. We compare that to the received MAC, and of course it's verified because it is a valid MAC. All right. We're talking about the message authentication code, not a MAC address. A lot of times people get confused about that. All right. Essentially, two types of hashing functions, MD5 and SHA. SHA-2 is the next generation of SHA. MD5 stands for Message Digest 5. Message Digest. Then it takes an arbitrary amount of data and it generates a 128-bit digest. We take an arbitrary amount of data and we generate a 128-bit digest. SHA-1 takes an arbitrary amount of data and generates a 160-bit digest. So it's actually considered to be stronger because of the key space. Remember, these hashing algorithms use keys. What is key space? What's another term that we can use to describe key space? Key length. Right? Think about it. Here's a description of key space. Your PIN code for your ATM card. If you had a 2-digit PIN code, it would be far easier to deduce what your PIN code is than if you had a 10-digit PIN code. Right? The key space is essentially the number of iterations of a key that are unique, or the iterations of unique keys. Now SHA-2 uses a much larger key space, 224 bits, 256 bits, 384 bits, and 512 bits. SHA-2 has pretty much been adopted as the standard for encryption by the powers that be. Is SHA-2 used in OpenVPN? Well, it can be, right? Both MD5 and SHA can be used for VPNs. It depends on how you define the VPN. IKE is not VPN. IKE stands for Internet Key Exchange. And what IKE does is it allows us to establish our VPN properties. There are two phases to establishing a VPN, which we'll see in the next chapter. We're going to do VPNs after this, but there are two phases in establishing a VPN. Number one, you have to do something called the Security Association Establishment. You have to derive the bulk encryption key, your shared secret key. So Internet Key Exchange is that process of establishing your bulk encryption key. It is not VPN. It is the first phase of VPN. Okay? OpenVPN is just another way of implementing VPNs. There are many, many types of ways of implementing VPNs. GetVPN, DMVPN, IPsec VPN, SSL VPN. All right? So that'll probably become more clear as we go into the VPN section, which is next. He said, yeah, I did some research about them in the past. Okay. Unfortunately, we don't get into the details as much as I'd like to in this class. We don't have the time. But we are going to look at VPNs in the next chapter, and hopefully you'll have a better understanding of the difference between IKE and actual cryptography, or VPN, confidentiality. All right? Now we know what encryption is, right? Encryption is the process of taking some plain text amount of data and then encrypting it using some algorithm, whether it's DES, triple DES, AES, IDEA, Blowfish, Twofish. There's a whole bunch of different encryption algorithms that exist. Some of them are symmetric, some of them are asymmetric. Okay? Question? Tell me, is it true that IKE2 is used mostly in local networks? No. I'm not sure what you mean by that. IKE2 is used in VPNs, period. Local or remote.
Isn't it Internet Key Exchange?
It stands for Internet Key Exchange.
So it's not going to be local.
Hmm?
But it won't be just local if it's an Internet key.
Well, the whole point of IKE is not to establish a specific type of VPN. It's to establish a bulk encryption key. Yes, but remote is preferred because more secure, as I knew. I guess, Bernard, I'm not sure exactly what you're referring to there. But we're not quite to the VPN section yet. So let's hold off on that until we get to the VPN section. All right? Hopefully that will help answer some of those questions. Okay? Encryption is the process of taking data, right? Plain text data, running it through some sort of encryption algorithm, and generating something called ciphertext. Okay? Now there are two types of encryption techniques that exist, symmetric and asymmetric. A symmetric encryption algorithm uses the same key to encrypt as it uses to decrypt, whereas an asymmetric algorithm uses one key to encrypt and another key to decrypt. We generally would use a private key to encrypt and a public key, a public key to decrypt. All right? Or it could be the other way around. You could use a public key to encrypt and a private key to decrypt. It depends on what your goal is. We'll talk about asymmetric encryption algorithms a little bit later on. The security of an encryption system, the security of your encryption algorithm is really based on one thing, the key length or the key space. The function of cryptanalysis is finding a way to essentially identify that key in a cryptographic system. And there are many, many different ways that we can go through and break cryptographic systems. All right? There's side channel attack, there's brute force attack, there's known plain text attack, there's known ciphertext attack. There's lots of different ways that you can actually analyze and try to break encryptions. The algorithms that we use are published. They're not secret. Everybody knows how AES works. Everybody knows how DES works. Everybody knows how triple DES works. And they're simple mathematical functions. So it's not the algorithm itself that makes the cryptographic system secure. It's the key. There's a new thing out now called quantum encryption. And it's actually quantum key exchange. Because really it's the key that's the most important thing. Encryption technologies are no longer going to use math, they're going to use physics. Quantum cryptography actually uses photons, polarized photons, to derive an encryption key instead of a mathematical function. Most encryption keys right now are derived through a process of factoring very large prime numbers, which computers for some reason just can't do very well. All right? We tend to focus all of these derivation processes on mathematical functions and not physics functions. Right? It's really kind of beyond the scope of this class to get into those kind of details, but we'll talk about some of these components. Cryptographic attacks, brute force. That's probably the one type of attack that you guys should understand the most, right? Brute force is just keep trying different keys over and over again. Try a key, try a key, try a key, try a key. And hopefully eventually you figure out the right key. All right? But of course, the longer the key, the harder that type of attack becomes. What is a ciphertext only attack? Any ideas what a ciphertext only attack might be? Yes?
You have the ciphertext, which is created after decryption.
You have a ciphertext which is created after the decryption or encryption. But what does knowing the ciphertext allow you to do? Well, what you try to do is you try to generate other ciphertext outputs that have similar features as the ciphertext that you have. And if you can start to see similarities, you know how you derived your ciphertext output, so then you can start to infer how that ciphertext output was derived. Known plaintext is probably one of the easiest ways for cryptanalysis to work. What is known plaintext? You know the message. And if you know the message, because remember, the whole point of cryptanalysis is not to identify the plaintext, it's to learn how what the key is. All right? So if you know some of the plaintext, then you can start analyzing how that plaintext is encrypted, and you can generate or derive the key from that process. So lots of different types of attacks. We'll see some more about each of these. Birthday attack. That's based on the mathematical principle called the birthday paradox. You guys ever heard of the birthday paradox? It is almost a mathematical certainty that says that if you want two people in the same room to have the same birthday, how many people would you have to have in that particular room? Now, most people would say, well, with absolute certainty, you'd probably need 366 people, right? If you have 366 people, you're guaranteed that somebody's probably going to have the same birthday, right? Because there's only 365 days in the year. But the way it works is, and I'm not going to get into the formula, it's a 1 to the n minus whatever. There's a whole formula for the calculation, but what it ends up being is you only need 23 people in the room. You only need 23 people in the room for absolute certainty that somebody is going to have the same birthday. It's an interesting concept. Meet in the middle attack is where you know plaintext and you know ciphertext, and you work both ways to try and figure out what the key is. All right. I've been meaning to maybe possibly go through and update the slide to give you details on these kinds of things, but I haven't done it yet. I think I probably will for the next class. It's an interesting topic, right? Cryptanalysis is very interesting, but on this exam, they don't really get into any cryptanalysis on the exam, which is why we haven't really gone into a whole lot of detail on it. All right? Now, like I said, modern encryption techniques today use public algorithms like AES or triple DES and secret keys. The algorithm itself is not secret. Now, I will say that the federal government probably does have algorithms that they use that nobody knows. Right? I mean, cryptography's been around since the Roman times, probably even before that. The cryptographic processes that we used back in the day were much simpler. They were things like substitution ciphers or transposition ciphers. Right? What's a substitution cipher? You take a combination of letters and you substitute them with another combination of letters using some sort of substitution box or some sort of substitution process. Transposition ciphers where you mix things up. Like the third letter of every word becomes the last letter of every word or something like that. All right? Now, encryption techniques are much more complicated today than they used to be. I have to show you this because I think it's really cool. I'm not going to go into detail on this because it will take forever. And we don't have forever. We only have about 30 minutes. So, but I do find it extremely fascinating. So I'm going to show you this. Maybe. God, I hate this, man. It's ridiculous. Let me go about this a different way. Let's go here. Let's go here. Let's go here. Let's see, 723, 71, 715. It's this one. Trying to get to the cryptography section. Oh, it's domain 3. Never mind. Let me go to domain 3. I don't know why it's taking so freaking long. Okay. A couple of things I want to show you in this slide deck, but some of this stuff we've already talked about. Plain text or clear text, natural message, ciphertext, encrypted message. Crypto system, the whole process of encryption. The algorithm, the key, everything. Encryption, changing plain text into ciphertext. Decryption, the opposite. Crypto variable is your key. That's what's going into the cryptographic system, etc. All right? Just kind of refreshing some of this. The algorithm is the process in which we use to do the encryption process. Cryptanalysis is the study or attempt to defeat an algorithm. Cryptology is the science that deals with hiding or disguising information. Collisions, we saw that term in the CCNA security material. It occurs when a hash function generates the same output for different inputs. That would be very bad, wouldn't it? If you had different hash inputs or data inputs that resulted in the same hash output. That should not happen. Key space, the size of your keys, right? And in this case, size does matter. Hash function. We talked about hashing. I'm not going to actually do anything on this slide because we talked about this stuff. We don't care about digital certificates yet. Here's a good term to know. Work factor. The whole goal of any cryptographic system is to make the work factor so great that breaking into that cryptographic system is not worth it. Work factor is how much time is required, how many resources are required to actually break a cryptographic system. No cryptographic system is 100% foolproof, period. The goal is to ensure that it takes too long for us to break a system. Initialization vector, we can talk about that. It's kind of a little bit beyond the scope of this class. Avalanche effect, right? We saw that term. When minor changes in either the key or the plaintext has significant changes in the ciphertext. That's actually a good thing, right? You want to be able to make minor changes in the key or minor changes in the plaintext to generate this massively different ciphertext. Okay? Substitution and permeation, we're going to talk about that. Transposition cipher, I mentioned that, where you take letters and you reorder them. Substitution cipher, where you take letters and you replace them. The whole idea here is to add confusion. This is not what I wanted to show you, but it is interesting. This is the one domain that makes CISSP very interesting. The rest of the domains suck balls, but this domain is pretty good. All right? Anybody have a CISSP? Anybody ever taken a has ever heard of CISSP? It's a tough one.
Yes, it is.
It's a tough one.
Very tough. I stopped the second try, so stop.
Says 6 to 8 hour exam. Yep.
However, our firewall guy did it 5 times.
5 times did he make it?
Good time? Well, maybe I should keep going. Twice.
It took me twice.
I didn't pass, though. I won't do it again.
No. It's a tough one. Cryptographic XOR, we don't have to get into this, but the exclusive OR operation is common to just about every encryption mechanism that exists. It's a Boolean function where you take 2 inputs and it results in an output. Basically, it's if both numbers are the same, it's a 0. If the numbers are different, it's a 1. Simple enough. Because when you're doing cryptography, there's a lot of mathematical operations that take place. Work factor. Let's see. I want to show you something that I think you guys will find very interesting. I wrote this whole course. I'm very proud of it. But this is kind of interesting. These are the work. Essentially, as of today, what we've defined as the best cryptographic algorithms that exist, right? The periods they're talking about is the workforce period or work time period that you would have to take to break the to decipher the key. Triple DES, that has a 112-bit key, 2011 to 2030. So actually that's already been cracked. AES 128, probably 2030. AES 192, much greater than 2030. AES 256, much greater than 2030. I don't know what they mean by that, but I mean,
At the time of this writing, that's when it would be, you started on it, that would be when it would be correct, right? That it?
yeah. But that's not what I want to show you. I want to show you AES. You learn all about all different kinds of encryption methods. And okay, here's the birthday paradox.
Oh. Speed reading, I told you, I failed that course. Speed reading course, I failed that.
Yeah, I know. Done? Okay. So the birthday paradox. Mathematical condition indicating the ease of finding two people with the same birthday from a group of people. 365 possible birthdays in a year. Yes? Everybody agrees with that. Of course, we're not taking into account leap year. All right? You would need roughly 183 people for 50% probability that two people share the same birthday. That's the assumption, isn't it? Because that's about half the year. You know, and as you go above 183, you expect that percentage to rise. But actually, if you have 23 people or more in the same room, that gives you greater than a 50% probability that two of them share the same birthday. And here's the reason why. 23 people is not just comparing 23 days. Because you're comparing your birthday with 22 people. You're comparing your birthday with 22 people. You're comparing your birthday with 22 people. Right? It's like saying you have OSPF adjacencies, and only having 5 routers means you only have 5 adjacencies. That's not the case, is it? If you had 5 routers, you would have 2 to the power of, or whatever that formula is, n to the n minus 1 divided by 2 power of adjacencies. Because you would have adjacency with 4 people, you would have an adjacency with 4 people, you'd have an adjacency with 4 people, and so on. That makes sense? So essentially, just with 100 people, you have a greater than almost a 100% chance that 2 people are going to share the same birthday. All right? By the way, if you put 23 in the formula, n times n minus 1 divided by 2, that gives you 253. That's the value that you get. All right? Ciphertext only attack. We saw a reference to that in the slide. Ciphertext only attack is the most difficult because essentially you have the information that is easily available, isn't it? Because what's sent across the clear channel in cryptographic processes? The ciphertext, right? So this is essentially the most difficult type of attack because basically you're just basing the attack on information that's readily available. You take the unintelligible data that you think is important, the encrypted data, and then you start to try to derive the key by trying to duplicate that encryption. All right? As you start to see trends or statistical commonalities between the data, the ciphertext you're generating and the ciphertext you have, then you can start to derive the key. But what changes in order to prevent that from happening? Are keys static? Keys are not static. They're dynamic in nature. Keys change. Key management is a big part of any type of cryptographic system. We rotate through keys as part of the process. Known plaintext makes your attack very easy. Because in known plaintext, you know ciphertext and plaintext versions of the message. So the idea here is now you know the plaintext, you know the ciphertext. What you're trying to derive is the crypto variable in between, which is the key. All right? Again, not stuff I wanted to show you, but I figured we might as well take a look at it since it was in the chapter. Let's see. Very interesting course, at least this domain. There's some pretty diagrams I did in here too, so this will give you an idea of how these cryptographic functions work. Substitution ciphers, transposition ciphers, rail fence. This is the algorithm that's used for service password encryption. Some French dude. All right, we're almost there. Almost there. Okay. We can look at the pretty pictures. Those are easier to understand. So in a symmetric algorithm, we take plain text, we encrypt that plain text with a cipher key. The ciphertext is what's sent over the channel, and of course the receiver has the same key, and they're going to perform decryption with that key. This is what we call a symmetric encryption process. The most popular symmetric encryption process is what? It's used every day in VPNs today. AES. That's right. AES is a symmetric encryption process where you have the same key to encrypt as you have to decrypt. Triple DES is also a symmetric encryption process. All right? So if you can imagine then, get past all this, DES, was based on the Lucifer algorithm. I like that. 1977, been around for a while. All right. Now, when it comes to cryptographic algorithms, we also have this thing called block modes, right? There's ECB block mode, there's counter block mode, there's a whole bunch of different block modes. And essentially the block mode defines, first of all, whenever encryption takes place, especially with a block cipher like AES or triple DES, you take a certain amount of plaintext data, usually it's about 128 bits of data, and you encrypt that data one block at a time. So your plaintext might be thousands of bytes of data, but you're actually only encrypting one block at a time. ECB, which is the electronic codebook block mode, just takes essentially each block of data and encrypts it individually. Right? So plaintext block 1, maybe it's 128 bits of plaintext data, goes through the algorithm, and out comes your ciphertext. Then block 2, then block 3. Here's the problem though. If you can start to capture enough of those blocks of data, you can start to see patterns. And we're talking about a lot of blocks of data. There's nothing random in this. Even the key is the same for each encryption block. So if you can start to capture enough of those blocks of data, you can start to derive that key because you start to see common themes in the ciphertext. Now, that makes it sound very simple. It's not that simple at all. Trust me. It's much more complicated than that. Okay? So we don't really use ECB anymore. We use CBC, Cipher Block Chaining Mode. And this is what Cipher Block Chaining Mode looks like. You take your original block of data, your plaintext block M0, you inject something called an initialization vector, which is basically just a random number. That ID is actually generated by a random number generator in the cryptographic process. That circle with a plus through it, what is that?
Aspirin tablet.
Aspirin tablet?
I can use on it. I think it-
That's an XOR operation. That's the symbol for mathematical XOR. So you take your plaintext block, you XOR it with your initialization vector, which is usually a 128-bit string or 64-bit string. So the data that you're putting into the first block is already randomized. Then you encrypt it. You take the ciphertext block output from the first block, and it goes into an XOR operation for the next plaintext block of data. What does that do for us?
Mix it up.
It makes it completely random, doesn't it? Every ciphertext output is random. It's based on the original ciphertext input. All right? Wait till you see AES. Now, stream cipher, or cipher feedback mode, sorry, even more complicated. This is a very modern type of encryption that we use for actually an AES and DES. Initialization vector goes into a shift register, n number of bits. So that might be a 128-bit initialization vector. You go through the algorithm, out pops a certain ciphertext block. You take half of that, which becomes the S bits, put in your plaintext block, do the XOR operation, get your ciphertext block. Those S bits go away. We move the ciphertext block over to the next level, and then we take n minus S bits and move it over to, that becomes essentially our variable operation. X1, Xi minus 1, and so on. It's kind of hard to follow this if you haven't gone to the class because the class kind of builds up to this stuff when we're talking about each of these pieces here. But you can see that the algorithms are complex, right? But mathematically speaking, they're predictable. This is a published method of cryptography. Now, the one thing I wanted to show you, should be coming up here any second now.
Cool. Ta-da.
Let me find it the other way. I could be going through about 50,000 slides. Oh, here it is. Hey, how about that? Rijndael algorithm. Rijndael algorithm is used for AES. We're going to look at it from the 128-bit perspective. So the input block of data is 128 bits of data. Notice that block there you see with the 32, the 88, the 31. Those are hexadecimal values representing our binary string of data. Now, if you add all those hexadecimal numbers together, you're going to get 128 bits of data. All right? So imagine, if you will, you have a complete string of plaintext data, and that plaintext data is being divided up into these arrays, or these blocks of 128 bits. Then you have your key, which also happens to be 128 bits in our example. That's our key, all right? Now that key was derived through some other mathematical process that we'll see, well, we won't see because we're not going to talk about that, all right? Now there are 4 steps, 4 mathematical operations to AES. Substitute the bytes, shift the rows, mix the columns, and then add your round key. And there are 11 different iterations of this as we go through the process. Now, I'm not showing you this because it's on the test. I'm showing this because I want you guys to get interested in this cryptographic process. This is one of the most popular and most widely used encryption standards that we see today. And it's relatively simple to understand. So this is the whole cryptographic system. You've got your initial round. The state that you see at the top is your plaintext. You got your ciphertext key. You're going to do an XOR operation where you're going to add the state to the round to that round key, the initial round key. Then you go through 9 separate rounds. So this middle section here is done 9 times. Basically, it's like here's a pile of dominoes. Mix them up 9 times. Right? But doing these things each time. And then you have your last round, which is essentially another round of mixing stuff up, and you get your ciphertext output. Okay? And that happens for every 128-bit block of data. So the initial round is to substitute. You have an S box. The S box identifies the substitution algorithm. The top box represents your plain text. The bottom box represents the substitution. So 19 became D4. A0, if you look at A, right, on the left column, A0 is what? E0, right? And then 9A is hard to follow, B8, right? You get the idea? So that's not a difficult operation, is it? As long as you know what that S box is, that substitution table, very simple operation. And that is the substitute bytes. That's the number 1 there, okay? Shift rows. Even simpler. You take that substitution block, you rotate over 1 byte on the second row, you rotate over 2 bytes on the third row, you rotate over 3 bytes on the fourth row.
By rotate, you mean just like the 30 moves over to where the A is?
Yeah,
so
notice that 27 BF B4, that's our substitution.
that's after, okay.
And then 27 moves over.
Right.
The 11 and the 98 move over, and so on.
Right.
That's the shift rows function. Now the mixed columns function is a little bit more complicated because we use polynomial math to do the mixed round column, or mixed columns, all right? It took me a while to figure this one out because it's not really documented very well. And I'm not going to go through it with you guys because you're not in the CISSP class, but it's just mathematics, right? There's a Galois field, and we have to go through and we have to take all of those binary values and do this finite field arithmetic where we're taking polynomials and multiplying polynomials and then coming up with bits, outputs, and then we reduce the polynomial. And in the end result is that row or that column becomes that column. And that's the whole math behind it. I spent like 8 hours trying to figure that out. But it's interesting. All right. And the end result is you get your different iterations of outputs to get your final encrypted output. All right. Oh, and then that's the key scheduler where you can generate your round keys. There's a whole bunch of different processes to generate the round keys. And looks like a fun class, huh? The answer is no. Yeah.
So that explains why most of the instructors I've had don't bother too much with cryptographic.
They don't bother what?
Explaining cryptographic
Yeah.
computation.
A lot of the CISSP instructors will just kind of
Skim over it.
skim over it. Yeah. That's the part that's fascinating to me. The part that's not fascinating to me is policy. And that's what most of the CISSP is policy. You know. All right. So you got symmetric algorithms, you got asymmetric algorithms. All right. Clearly, we just talked about this in a much simpler format. A symmetric algorithm is where we use one key to encrypt, we use the same key to decrypt. What is the inherent problem with this particular method of encryption?
Symmetric keys on both sides. So if I got one key,
Well, the problem is, how do you share that key? Right? How does the person that's sending the data let the person receiving the data know which key to use? It's not practical to statically configure a key, and it's also not recommended because keys can be derived. So we like to change keys so that we can't figure out what the keys are. All right? There's a process called the key exchange process, Diffie-Hellman key exchange process that's used for that. These are some of your symmetric encryption algorithms, DES, triple DES. This is the kind of stuff that you're going to be tested on, right? Not the math behind it, but the algorithms themselves. You know, what are they classified as and so on. Obviously, AES and triple DES, all the Rivest ciphers. Ron Rivest, that's a hairy bearded dude that invented a lot of cryptography. He's the guy that does RSA. RSA stands for Rivest, Shamir, and Edelman. Rivest is one of those guys. All right. Seal, idea, blowfish, two fish, three fish, four fish. No, red fish, blue fish. Yeah. Sounds like a Dr. Seuss novel, right? Okay. Quite simply, an asymmetric algorithm is when you encrypt the data with one key, but decrypt the data with a different key. Okay? Now, the reason that this is computationally expensive is because the keys are derived using the factoring of large prime numbers, and that takes a lot of processing power. What is the concept of factoring a prime number? In general, what's the concept of factoring a prime number? What does it mean to mathematically factor a number? It means what two numbers can you multiply to get that number? Those are the factors, right? Apparently, it's very difficult to factor large prime numbers. Why?
Because there's very few factors.
There's very few factors, right? So if you have an extremely large prime number, finding the factors are very difficult. And that's how asymmetric algorithms work.
See, you didn't think I was on you, did you?
No,
I'm much the pretty face guy.
if you say so. So Alice on the left, Bob on the right. So Alice has Bob's public key. Alice encrypts her data with Bob's public key. But the only way that the data can be decrypted is with Bob's private key, and Bob never shares his private key. What's missing from this process? Who can encrypt data and send it to Bob? Anybody. Because Bob's key is public. This is how SSL and HTTPS works. When you connect to a web server, the web server announces its public key to you so that when you send data to the web server, it gets encrypted with that public key, and then the web server decrypts that data with its private key, which nobody knows. Oh. Stuck to the side. That's how close I was. All right. So you guys understand the general concept, right? When you connect to a web server using HTTPS, you're using either one of two protocols. You're using SSL or you're using TLS. TLS is kind of the replacement to SSL, secure socket layer or transport layer security. And a web server has a private and public key pair. Now there's another piece to that. When the web server, let's say Bob is the web server, Alice connects to Bob. Bob sends Alice his public key. What else is used for that public key process? What else does getting Bob's public key allow Alice to do? Is there any kind of authentication? Because what is that public key? That public key is a signed certificate, right? You guys heard of something called PKI? Public key infrastructure? So Bob's certificate is not generated by Bob. Bob's public certificate is generated by a third party that verified that Bob is who Bob is. Called the CA, right, certificate authority. So Alice not only uses that certificate to authenticate Bob, because a third party, a trusted third party, verified Bob. That's what a guy with no arms and no legs in the ocean is called too, by the way. Bob. All right. We should make Alice Eileen. That's like a woman with no arms leaning up against the wall. Sorry.
Fellow one leg shorter.
Or Bob could be Matt, right? Guy with no arms, no legs sitting in front of a door. Yeah. Anyway, so Alice gets the certificate from Bob. That certificate is signed by a certificate authority. Alice trusts the certificate authority, so therefore Alice trusts Bob because the certificate authority verified Bob. But that's not the only reason that that certificate is important, because now Alice uses that public certificate to do encryption, and it encrypts all the plaintext messages with the certificate, which goes over the channel. Nobody can decrypt that because nobody knows the private certificate used to do the decryption. Okay? Does that make sense? That is the asymmetric encryption process. All right? Now, there's another way to do asymmetric encryption. Alice can encrypt her message with her private key, and then Bob can decrypt the message with Alice's public key. But this is only used for non-repudiation. This is not used for confidentiality. Why can we not use this for confidentiality? What are we decrypting with? We're decrypting with a public key. Yes? Everybody knows the public key. It's published. So anybody can decrypt that message. However, this is used for non-repudiation. What does that mean? Alice can't say she didn't send the message because the message was encrypted with Alice's private key, and only Alice knows that private key. And Bob can't say that he didn't receive the message from Alice because the only way Bob is going to decrypt the message is with Alice's public key. So this is used for authentication. It's not used for confidentiality. Two ways of using asymmetric keys. All right? Digital signatures are essentially what we just talked about. A digital signature allows us to attach a signature to a piece of data, whether it's software you're downloading or information that you're sending, that verifies the authenticity of the sender. Okay? Now, how does a digital signature provide for message integrity? How does a digital signature provide for message integrity? Any ideas? Because if a message is sent, it can be hashed using the signature. We talked about that in the very beginning of this chapter. You can actually use a digital signature to generate a hash. Of course, we know how digital signatures can be used for non-repudiation of transactions, because there's no way you can deny sending something if it was signed by you. Private key of the signer is used to create the signature because only the signer knows that signature, or only the signer knows that key. So you can tell the signer, sign this data with your private key. I'm going to decrypt it with your public key to verify that it was signed by you, and there's no way you can deny it because you're the only one that can sign it with that key because you're the only one that knows that private key. All right? So, we have a purchase order that we're sending. Now, we don't care whether or not the purchase order is in plaintext or encrypted. So in this case, the purchase order is being sent over our public channel in plaintext. I'm hashing the purchase order, which is used for message integrity. And then I'm signing the hash with my private key. I'm essentially encrypting the hash with my private key. So the 49ED0E, that's my hash. The E10D6200 is an encrypted version of the hash using my private key. Now notice the data is actually still sent in plaintext, but we're now sending the encrypted hash with the data. The only way to decrypt that hash is to use the public key of Alice. And if that works, that means we verified who Alice is, because the only person that knows the private key is Alice. And by verifying the hash, what did we verify? By verifying the hash, what did we verify? That the message wasn't modified. This is the same process as HMAC. But HMAC is used for symmetric processes. This is used for an asymmetric process where we've got a private and public key pair. Fundamentally, does this make sense, guys? The thing about cryptography that's the most difficult to understand is that there are a lot of frickin' moving parts. There are a lot of pieces to cryptography, and they all kind of do unique things. I guess you guys wishing you went back to CCNA now, huh? All right. What is it? Ah, it's lunchtime. Lunchtime.